The secret of your success lies in the power of choice. Silicon, silicon carbide, and gallium nitride power semiconductors come with very unique characteristics, offering different benefits. To provide the highest level of system performance in your application, you have to know what each of these technologies can bring to your designs. Silicon, silicon carbide, and gallium nitride, when to use them. Gallium nitride is a technology of choice at fast-switching frequencies, providing the highest efficiency and power density at an overall optimized system cost for power-hungry applications. Wide bandgap materials complement silicon solutions, pushing the envelope of power efficiency, size, and weight reduction further for even higher levels of performance and enabling new topologies. Silicon carbide can withstand high temperatures and harsh environments. In addition, the possibility to use standard drivers with it makes silicon carbide an easy-to-use option for improved performance compared to silicon. Choosing legacy silicon provides you with the best price-performance ratio. This mature technology addresses a large variety of use cases in which price performance is desired. We know that the choice is not easy, but as your trusted partner with our several decades of experience in power semiconductors, Infineon, the expert in all three power technologies, is there to help you. We are also a committed and well-positioned supplier to fully support your growth at the highest quality standards. Our ramp-up capability, as well as 300mm wafer fab for power semiconductors and continuous R&D investments in next-generation wide bandgap and silicon technologies, together with our technology know-how, is all there for your success. Choose from our broad power portfolio of high-quality, highly efficient, and ease-of-use products. Visit our website to learn more about wide bandgap technologies.
First, thank you for giving me the opportunity to give a presentation in this webinar series. So in my today's presentation, I will talk about my work when I were in Yokohama National University. So at that time, I would like to acknowledge Professor Kawamura and also Yasuhiko Miguchi, as at that time this work is supervised under Professor Kawamura, and we work together also with Miguchi. So in today's presentation, I will talk about the research at that time where we try to develop a high efficiency energy conversion system. So at that time, what I do is I investigate the possibility to achieve a high conversion efficiency converter by using the gallium nitride device. So the outline of my today's presentation is as follows. First, I will give introduction. So I will explain the circuit configuration of what we call as the high efficiency energy conversion system. And I will explain the basic operation of the converter. And then next, I will give the brief explanation about the control implementation for this converter, where we will use the deadbeat current control law with the outer voltage control loop. So this work is mainly developed by Miguchi. And in the third presentation, I will talk about the implementation of the three-level converter in this energy conversion system, where we using gallium nitride device, which we use the bare dies chip, and we directly reflow-soldered the chip on the PCB. And then next, we also implement some variable dead time to improve the efficiency. And then we do some loss analysis to see the loss distribution. And then we measure the conversion efficiency. And at that time, we can reach the peak efficiency of 99.81% at the output power of 1.7 kilowatt. And in the end of my presentation, I will give the conclusion. Okay, first, the high efficiency energy conversion system consists of a power converter, which in this case we use a multi-level converter, specifically 3-level converter. So in this 3-level converter, we use two half-bridge circuit, where the first half-bridge use two MOSFET S1 and S2, and the second half-bridge use two MOSFET S3 and S4. In the system, we use two voltage sources, DC voltage sources E1 and E2. And then there is a DC filter, L and C. And then we have an unfolding circuit, which is, we use the full bridge circuit, comprises 4 MOSFET S5 to S8. And then the system is used as a active front end, where it's connected to the grid with the grid connected inductor LG. So for the basic operation, first we can see the operation of the 3-level converter. When we want the output voltage VC is less than E1, so we always, so we always turn on the switch number 3 and always turn off the switch number 4. And then the switch number 1 and 2 are controlled using PWM, so that we can control the output voltage. And then when we want the output voltage VC is larger than E1, but smaller than E1 plus E2, in this case, we always turn on the S2, and we control the S3 and S4 using PWM. And then after that, we try to generate the rectified sine waveform on the capacitor voltage C. We call it the inverter voltage. So as you can see, first, the output of the 3-level inverter VSV is the PWM output with 3-level voltage of 0, E1, and E1 plus E2. And then the filter L and C remove most of the high frequency component, so that we have the rectified sine voltage on the capacitor voltage. And then the role of the unfolding circuit is to unfold this rectified sine, so that we can get a clean sinusoidal waveform. So basically, we turn on S5 and S8 when the capacitor voltage is in one cycle of in half cycle of the sine wave, and then in the other cycle we turn on S7 and S6 to give a negative polarity at the output. And next, for our experiment, we select the circuit parameters as follow. So we select the DC capacitor voltage E1 and E2 equal to 280 volt and 125 volt. And then we select the DC filter inductor and capacitor with the value of 2.43 millihenry and 8 microfarad. And for the grid connected inductor, we select the value of 3.77 millihenry, which is the percent impedance is around 3%. And in our setup, we use the grid voltage of 280 volt RMS with this grid frequency of 50 Hertz. Next, for the device selection of this power converter. For the 3-level converter, basically hard switching always occurs. So there is always a trade-off between on-state loss and switching loss. But because this is the multi-level converter, basically we can reduce the switching loss by reducing the DC voltage applied to the switch. So we can select a switching device with a relatively low on resistance, because the switching loss is not as high as the let's say the normal inverter, normal two-level inverter. So in this experiment, we try several wide bandgap power devices, where we use one power device SiC MOSFET from room, which have 17 milliohm on resistance. And we also try to investigate the possibility to use the gallium nitride MOSFET, which we use the gallium nitride with the voltage rating of 650 volt and current rating of 150 ampere. The on resistance is around 10 milliohm. And then for the unfolding circuit, because it's operate at a low switching frequency, where in this case is only 50 hertz, the switching loss is negligible. So in this case, we can select device with the lowest on resistance that available in the market. So at that time, we use the power module, which use multiple SiC chip inside, where this device, the on resistance is only around 3.8 milliohm. So next, I will give a brief introduction about the control theory that we use to control this converter. So first, we will analyze the converter itself. For this system, we can assume, or we can make an equivalent circuit as follows, where we can assume all the three-level inverter as only a switching network, and the LNC here is the DC filter, and the output we can assume it as a constant current IDC. Sorry, we can assume as the current source IDC. So for this equivalent circuit, we can derive the equation of this equivalent circuit, which is given by this equation, where the xt is the capacitor voltage and inductor current, and the parameters of A, B1, and B0 is given by this matrix. And then because we control always in the digital system, so we need to model the system. We need to model it inside the sampled data model. So in this case, in our control, we use PWM pulse, where the voltage pulse is in the center of every sampling time. For example, at sampling time from kt to k plus 1t, the PWM pulse is started in the center with the pulse width of delta t. From the equivalent circuit equation here, we can make the equation of the sample data model as given by this equation, where the parameters of f, g1, and g0 is given by the matrix here. Okay, and then we use the deadbeat current control law principle to control this power converter, where in this deadbeat current control law, we want the inductor current in the next sampling instant k plus 1t is matched with the current reference that we want. So then, based on this law, simply taking the second row of this of the matrix in this equation, we get the equation of the current control, and we replace the current control in the next sampling as our current reference. So then it yields the duty that we will apply, duty cycle or duty ratio that we will apply to the three-level converter, so that we can control it based on the deadbeat current control law. So the duty cycle is given by these equations. And then at the outer loop of the, and then from this deadbeat current control law, we add the voltage control as the outer loop to give the to decide the value of the current reference based on the voltage reference. In this case, the outer control loop use the proportional gain only to decide the current reference, where the equation is given as this equation. So KPV is the proportional gain for the voltage control loop. And the voltage control loop gain is designed by using the root locus method, where we can see the two poles converge here, and we select the value of the gain is close to the value where the two poles converge, which is we select the value of 0.06 so that the system is not oscillatory, but it still have a fast response. And finally, this is the complete control block diagram for the system that we use. So in our system, we control by giving the power reference to the system. So the system is active front end, so it can be operated as the in powering or regenerating mode. So basically, the converter can be operated as the inverter or rectifier based on the power reference value that we give. So from this reference value, we can calculate the current, the AC current that we want, and then we use the current controller, where in this case, we just use simple PI control to control the direct and quadrature current. And then from the current control, we get the value of the inverter voltage that we want the three-level converter to generate, where in this case, uh, the absolute value of the inverter voltage is equal to the DC capacitor voltage, where this DC capacitor voltage is the reference for our deadbeat current control law plus voltage control loop. So then using this voltage control law, we can decide the duty ratio, and then this duty is used to control the operation of the three-level converter. So that part is the control that we use. And next is I will talk about the implementation for the three-level converter. So basically, we want to implement it so that it can achieve as high efficiency as possible. We use the wide bandgap power device, but we need to implement it properly so that we can achieve the full potential of the wide bandgap itself. So to achieve the full potential, especially when we use the gallium nitride, we want the switching transient to be as fast as possible. In this case, we want to have a we want to use very low gate resistance so that we can reduce the switching loss significantly. To achieve a stable operation with high switching transient, basically we need to have a small power commutation loop so that the parasitic inductance in power commutation loop is very small. So in this case, we have two half bridges where each of half bridges have their own power commutation loop. For example, for the low half bridge circuit, for the power commutation loop is the loop which consists of C1, S1, and S2. And then for the upper half bridge, the power commutation is the loop that consists of S3, S4, and C2. But because of our circuit topology, S2 is inevitably inside the power commutation loop of the upper half bridge. So in the beginning, we get the power, we get the three-level converter from a manufacturer that was built by using the half-bridge power module. In this case, because it's a half-bridge power module, so the S1 and S2 is inside the one module, and S3 and S4 is inside the other module. And in this case, it's impossible to achieve a small power commutation loop for the upper half-bridge because S2 is inside the power commutation loop of the upper half-bridge. In this case, then we cannot put C2 very close to S3 and S4, which is basically typically in the power module, we can install the DC snubber capacitor inside of the power module itself. But in this case, because S2 is needed to be inside the power loop, so the C2 or the DC snubber of this half bridge was removed. So in consequence, yeah, there is a big parasitic inductance. Then we cannot we cannot switch the upper half bridge in a very fast manner. So in that case, we need to use relatively large gate resistance. So when we use small gate resistance, there will be big noise in the gate voltage, which resulting in the wrong switching pattern, and it damages the MOSFET itself. So in this case, then we try to implement it not using the power module, but we try to rearrange all the components so that we can achieve the smallest power commutation loop as possible. So in this case, we try to reflow solder directly the bare dies of the MOSFET directly on the PCB. So this shows the process. So we use the gallium nitride bare dies and we reflow soldered it directly on the PCB. So in this reflow soldered process, we can inspect the active solder area, and we can also see if there is if the solder joint have a good quality where there is less air bubble. This inspection we can use X-ray, and we can see through under the bare dies itself. And then one of the important point when we design using bare dies is that we need to connect the body of the HEMT to the source so that we can get the stable threshold voltage. So in this case, we attach the copper foil to connect the body to the source terminal, and then we solder the copper foil at the body and the source pin so that we can have a stable and good connection. And then we put in the end of the manufacturing process, we put the heatsink directly on the top of the body of the MOSFET to help reduce the temperature at the high power operation. And this figure showing the PCB implementation. So in this case, we try to further reduce the parasitic inductance in the power commutation loop. First, we try to use the magnetic flux cancellation effect, where for each power commutation loop, for example, for the switch for the lower half bridge S1 and S2, we put the both switches at the same position at the top and bottom layer, and then we use white copper trace at the top and the bottom layer sandwiches so that the current flow in such a way that we can achieve the magnetic flux cancelling effect. And also by using this direct reflow soldered bare dies on the PCB, we can put the gate drive circuit as close as possible to the gate source terminal. And yeah, we design the gate drive properly also so that there is less interference between gate drive circuits. And then by using this approach, we can reach the limit of the gate drive IC, where where it can produce the maximum current so that we can achieve the fastest switching speed for the gallium nitride power device. In this case, we use the gate resistance for turn on is 20 ohm and turn off is 2 ohm. And that's for the three-level power converter implementation in the physical implementation. And then next for controlling the operation. So as we know that we use a gallium nitride which have a relatively low on resistance. So in this case, the COSS or parasitic output capacitance is quite large. So the large COSS will cause a relatively uh, big switching loss, especially during the dead time when the current is low. So then in this case, we implement the variable dead time technique to reduce the loss from the COSS. For example, during powering mode, we see only the lower half bridge S1 and S2 with the DC voltage of E1. So powering mode means that the power or current flow from the DC to the AC side. So for example, at time before T0, so S1 is on and current flowing inside this loop. And then during the dead time, it's between T0 to T1. So we turn off both S1 and S2. But because of the direction of the body diode, so the current still flowing through this loop. And then when we turn on the switch S2 at T1 between T1 and T2, then the current start to flow from the upper switch S2. So in this case, during the dead time, the current is always flowing through the body diode of the MOSFET. So in this case, we always set the dead time as minimum as possible that allow us to operate in a stable way. In this case, we set the value is at 50 nanosecond for the dead time of the TD2. Well, if we consider the other dead time, TD1, is when at first the current flowing through the upper MOSFET, and then we turn off the upper MOSFET at T2. So in this case, because the current direction and the position of the body diode is not in the same direction. So once we turn off the S2, then the current start to charge the COSS of S2 and discharge the COSS of S1. Depending on the value of the current, so it will change the rate of the charging and discharging of the parasitic output capacitances. So in this case, if we set the TD1 is too long, so mainly we can completely charge and discharge the parasitic output capacitors, then the current will flow through the body diode before we turn on the switch. So this will cause the loss. Yeah, since the gallium nitride have a relatively high voltage drop during the so-called the body diode operation. And then if we select TD1 is too short, so we turn on the switch S1 before we completely discharge the COSS. So in this case, then we will produce the loss from the COSS. So basically, then the point is that for the TD1 during the powering mode, we need to vary the dead time depending on the load current so that we can always turn on the MOSFET S1 just after the COSS of the S1 and S2 is fully discharged and charged. So in the same way for the regenerating mode. Basically, in summary, the same phenomena occurs during the powering and regenerating mode. But during the regenerating mode, for the TD2, we vary the dead time. We not fix it always at 50 nanosecond, but we need to vary depending on the load current so that we can always turn on the S2 when we just fully discharge its parasitic output capacitor. And for the TD1, we set the dead time at as low value as possible, which is in our experiment, we set it at 50 nanosecond. So next we do the experiment. First, to show the effect of this phenomena in the dead time. So we use this, this is the circuit configuration that we use. And this show the experimental setup. And this is the circuit, the GaN PCB that we developed. And this show the experiment to verify the dead times. So the top one show when we set the dead time is too long. For example, we set the dead time is at 600 nanosecond. We can see that maybe, yeah, we can see that this is the body diode is turned on, and this is for TD2 during the powering mode. So if we just set the dead time at the constant value, so we want to reduce the loss from this voltage drop of the body diode, which is, in this case, is quite large, which is around 6.1 volt. So then we basically, we want to reduce this loss. So we need to set the dead time with the lowest value as possible. So in this case, we set the dead time at 50 nanosecond. So we can reduce the loss producing by this duration. And then for the TD1, if we select the dead time duration too long, then we can see the body diode start to conduct here, which added the loss. And then if we select the dead time is too short, then before we can completely discharge the output parasitic capacitance, we already turn on the device, and all the energy that's stored in the capacitor will become lost. So basically, we need to set the dead time when we just fully discharge the COSS, so that we can turn on the device when the voltage is just reached to 0 volt, as shown by this graph. This is the same as the showing the dead times, confirmation of the dead time during the regenerating mode. In this case, instead of TD2, so we can see the TD1 got affected by the additional loss because of the body diode. And then to reduce this loss, we need to reduce the dead time, which is in this experiment, we set it at 50 nanosecond. And then for the TD2, we need to select the dead time properly so that we don't select the dead time too long where we have additional loss from the conduction of the body diode, or we don't select the dead time too short where we get additional loss from the energy stored in the COSS. So by using this technique, we can select the proper dead time. And then next, we do the experiment by using the deadbeat current control law plus voltage control loop, and also by implementing the variable dead time. We try to measure the power conversion efficiency, and we do some loss breakdown approximation. So basically, we measure the operation of this high efficiency energy conversion system when we use variable dead time and when we not use variable dead time. So by analyzing the measured loss, we can see the effect of the variable dead time, where because at very low current we use a relatively long dead time, then we can eliminate the additional loss from the COSS as shown by the tail at the low power on the figure on the left. And then also the variable dead time also allow us to, I'm sorry, so another important factor that can be seen from this waveform is that by using, so the left waveform showing the loss breakdown when we use the uh, gallium nitride in the power module. So in that case, we cannot achieve the high switching speed. And then the graph on the right showing the loss breakdown when we use the gallium nitride is directly reflow-soldered on the PCB. So we can reduce the gate resistance to achieve the higher switching transient. Then we can see the red portion in this loss breakdown can be significantly reduced, where this red portion showing the switching loss of the three-level power converter. And this figure show the measured efficiency. So by using the reflow-soldered GaN on the PCB and using the deadbeat current controller plus voltage control loop, we can achieve the power conversion efficiency of 99.81% at output power of 1.7 kilowatt. So yeah, that's conclude my today's presentation. So as a conclusion, so in this presentation, first I talk about the implementation of the three-level power converter using GaN bar dies. So the approach that we use is that we reflow solder the GaN bar dies on the PCB to reduce the switching loss. And also we implement the variable dead time to reduce the loss from the CUSS, especially at the low voltage range. And as a result, by doing this implementation, we can achieve the peak conversion efficiency of 99.81% at the output power of 1.7 kilowatt. Okay, thank you. Do you have any question or discussion? Feel free to ask me directly.
Okay, thank you, Dr. Hardy. So it's a very interesting presentation. So while we are waiting for the question, so I have some question for you. So I'm just curious because I don't understand clearly. So what application your system can be applied to?
In this case, the system can be used for any active front-end application. So basically, it can operate as the inverter or rectifier. And also in the past, this topology was the research was done for the EV application, where the E1 and E2 is the battery in the electric vehicle.
Okay. So, for example, the vehicle EV, right?
Yes.
Yes. So now I can see that in this figure, yeah, I have a question for this figure. So we can see that we have two stages, AC/DC and the DC/DC, right?
Yes. This is, yeah, correct.
Yes.
AC to DC and DC to DC.
Yeah. So I think that this presentation maybe focus on the DC/DC only, right?
Yes, true.
Yes.
Because on
So this DC/DC is the three level DC/DC, or I don't understand.
so yeah, if we see from here, this is the output of the DC-DC. Yeah. So the output is either 0, E1 plus E1 or E1 plus E2. So until
Okay.
this part is 3 level. Yeah.
And also this is the bidirectional converter.
Yes, it's bidirectional.
Yes. So, can you show me any reason you choose the 3 level? So how about the DC-DC, just the 2 level or the conventional DC-DC? Do you conduct any comparison before?
I think in the previous research in the team, they already do some study.
Yes.
Yeah, I think one of the benefit of using multi-level, we can reduce the switching loss because we reduce the voltage. But also but we don't want also to use too many levels. As we can see, if we keep increasing the half bridge, so it will be quite complicated to implement the circuit. So one thing for the additional half bridge, we add, let's say at the top. So then the power commutation loop become bigger and bigger. So then it's very difficult to achieve the high switching speed for that half bridge. And also then we need more DC sources for that circuit. Yeah.
Okay. Also, just myself. Last question. So what the power rating of your system?
In this system, the aim is for up to, I think, around 5 to 10 kilowatt. Yeah.
Okay, 5 kilowatt. So we have the two questions.
Okay.
From the Tiêu. Can you directly ask the presenter?
Yes,
Tiêu
yes,
ơi.
I can.
Oh, okay.
Yeah.
Hello. Yeah.
Okay. Firstly, thank you so much for the presentation, and I have two questions. I see that you use very much the switching the MOSFET in here, and I am curious about the switching frequency of them. Firstly, about I see that you use the GaN device for the
Yes.
project. So, what is your the gate driver solution you use? And I have two questions. Can you answer it for me?
Okay. So with your question is the gate driver. Am I right? For the GaN device.
Yes.
Okay. So in our gate driver, it's not shown in this presentation, but basically in this implementation, for the gate driver, we just use isolated gate drive circuit for each switch. So each switch have their own gate drive circuit, and we don't use the bootstrap topology for the gate driver. So we have 4 isolated gate driver circuit for each GaN devices in this case. And it's just simple structure where we use from the controller, there is the optocoupler it's not optocoupler, some digital isolator to isolate to give the isolation to the gate driver IC, which fit the power or which generate the gate voltage for each switching devices. So
Okay, thank you.
Yes.
Yeah, but I see that the frequency you are applying in here is a 50 hertz. So it's really needed for the GaN. But
So
I think GaN is apply a very high frequency.
The 3-level converter we use actually we test at various switching frequency. Sorry, the 50 hertz is only for the unfolding circuit. And for the 3-level converter, we still operate at the tenth of the kilohertz range. So this one we operate at a higher switching frequency. So we do investigation at, I believe it's in between 10 kilohertz to 50 kilohertz.
Oh, I think with 10 and 50 kilohertz, in my opinion, I use the SI or SIC instead of the GaN.
Yeah.
Because with the infinite solution, I can choose the the device that can that have the with the SI material, and I have RDS on is less than 3 milliohm, and the switching frequency can be up to uh, 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 100 kHz. So I am curious about why you can why can you why are you why you are using the GaN device instead of the SI device.
Okay, yeah. This is
Yeah.
about the device selection. Yeah. So yeah, basically there is one point in the research that we try to investigate which devices is best for this application. So we do also some analysis, or we do experiment and implement several power converter tests where we use also SiC devices and compare the efficiency. Yeah, I think it's back to the optimization for the device selection, where you have the trade-off between the conduction loss and the switching loss. So I think, yeah, it's not necessary we need to use GaN, but I would say might be also SiC seems a better choice compared with the silicon, because I believe that wide bandgap device have a better figure of merit, where in this figure of merit I would refer to the ratio between the on resistance and the COSS, or the parasitic capacitance. So yeah, then first we need to select the device which have the best figure of merit, and then after that we need to select proper device uh, device with proper on resistance, so that we get the optimum loss, which is the sum of the conduction loss and the switching loss from the COSS.
Yes, I got it. The last question the last question is the gate driver in the gate driver design. You mentioned about the flux cancellation, and
Yes.
uh, and the way the way you implement that is you uh, can you repeat that repeat the flux cancellation as you mentioned?
Sure.
Yep.
Okay.
Yes, in here you have the flux cancellating effect. So can you have uh, the short re-explain about that?
So yeah, basically for the power loop, for example, uh, for the S1 and S2, so the power loop from the top side will flow through the C1, and it will return through the bottom side of the PCB. So then the current will flow, let's say current will flow down on the top side and will flow up at the bottom side. So then this different current direction at the top and bottom side of the PCB trace with uh, with the very thin PCB trace will help us to reduce the inductance caused by the parasitic inductance caused by the length of the PCB trace. So it's simple. It's layouting of your PCB trace basically. Yeah.
Yes. Yeah. Yes, I got it. Thank you so much for your explain. Thank you so much.
Okay, no problem.
Yeah.
Okay, so now we have the question. So now we go to the question from the Dr. Tiên. Tiên ơi.
Yeah,
Okay.
yeah. Hi, Dr. Hardy. Thanks for your very detailed and informative presentation.
Oh, hello.
Uh,
Yeah.
yeah. So, yeah, I have a question in terms of the application. So for the DC side, I see there's two DC source, and can we use can we use a PV or which type of source for the E1 and E2?
I think yeah, you can use any type of the source. Yeah, for this application. Yeah. Yeah. In our investigation, actually we not really specify the application, and it's really open to any kind of application, as long as you can get stable multiple DC input voltage source. Yeah.
Okay.
Yes.
And have you why you select the three level converter? It's not like a NBC or T-type NBC. Why you use this topology? Do you have a comparison with the NBC?
Yeah, I think in the previous work, they did the comparison already. I think
Okay.
between this type and also the T type. One of the conclusion is that I think yeah, if we use T type, so basically the power loop for the lower and upper, it consists of at least 3 switching devices. Yeah. So that's one of the design consideration, and also another point, I think for the on resistance loss and other part, they are almost similar, I believe. Yeah.
Okay.
Yeah, there is
And
some publication about the comparison. I think I can get back to you and share the publication. Yeah.
thank you, thank you. And the question about the bare dies GaN. So can you
Yes.
go to the BCB figure?
Okay.
Yeah, this one. So I see there's a lot of veer, a lot of veer. So this veer is responsible for the thermal transfer the thermal from the bare dies to the heatsink, right?
Also, yes, yes. And basically, yeah, we want to have a wide copper plane, so we can utilize the top and bottom copper plane. Yeah.
And why do you use the vias from the bare dies? I mean, go directly from the bare dies to the heatsink. Why you make the via outside of the bare dies?
Sorry,
Actually,
you mean this via?
yes. I mean the via under the heatsink. Do you have a via under the heatsink?
In this case, under the heatsink, there is no via. Yeah, under the heatsink, we put the heatsink directly on top of the power device, on top of the bare dice itself. Yeah.
Oh, okay, okay. So okay, it mean the metal is also like a bare dice, right? It's not.
Yes.
Yeah, okay, okay, okay. Yeah, this is the
Maybe
first
you're
time.
concerned about isolation. Yeah, there is the thermal conductive tape here, which give us the some, but actually they are have the same potential. Yeah, there is no problem also for electrical isolation. But yeah, we put some thermal conductive tape here because yeah, you notice the surface is not even. Then we need to put the heatsink on top of this paradise.
Yeah, I never work with the bad eyes. I just think the bad eyes mean inside the BCB layout. So we need the via to transfer the heat to the top and the bottom of the BCB. But when I see the figure here, it mean the switch it mean on the surface of the BCB, right?
Yes, directly on the surface.
Okay. And the question about the gate driver. So, have you ever tried the GaN device with the bootstrap gate driver?
Yeah, in this case, we haven't tried that yet.
Okay. Yeah. And yeah, thank you. Yeah, thanks for your.
Thank you for your question.
Yeah, it's pretty good. Yeah.
Okay, so Dr. Chung have a question. So please, Dr. Chung.
Hi, Dr. Setyadi. Thanks a lot for presenting. I have questions, but not regard to technical things because I'm not expert in the field. But just I see from biography that you are working for Rondroy Research Center, and I'm working for R&D Research Center of ABB in Germany too. And I just want to ask, like, what do you like or dislike when comparing R&D in industry and academia?
Thank you for the question. Yeah. Yeah, I think now I'm work closer to industry, so I think especially for my application, it's more for high power now. So in scale of 200 kilowatt above. So and what we do now in industry mainly is prepare the prototyping product with technical readiness level of 4 or beyond. So in this case, I feel maybe in industry it's more we don't really push or try to implement the latest technology, let's say, because we want to select the mature one and really proven technology. And another things maybe maybe that's the main different things. In industry, we mainly develop the product that is ready for the market. But yeah, in research, we can try to push the boundary and try to find maybe new solution or some, of course, in industry, we sometimes we need to find a creative approach also to solve the problem, but it's more to the practical side. I feel, in the academia, we push from the more theoretical point of view. But I would say both are interesting and you can always learn from both sides.
Yeah, exactly. Yeah, I fully understand and fully agree. Yeah, you are right. Same experience with me. And what do you prefer? Academia or industry?
I hope maybe if it's possible in between. So if there is collaboration between industry and academia, so then we can work on both sides.
Thanks a lot for sharing. I mean, it reminds me in Switzerland there is research funding named Bridge, mean the bridge connecting between basic science and applied science. But thanks a lot for sharing and nice to have talked with you. Yeah, have fun.
Yeah, nice to talk with you.
Yeah, thanks.
Thank you. Yeah.
Okay, so because due to the time limitation, so we have I think that we maybe move to the question from the Dr. Meng, maybe the last one to ask the presenter. So please, Dr. Meng.
Yeah, thank you. So, thank you for your interesting presentation, Hadi. I have just one question for you. You hear me well?
Sure, yeah.
Yeah. So could you move forward to the last slide, please?
The conclusion or
Yeah.
okay.
The previous one, just the previous one.
Okay.
Yeah. So we can see here the conversion efficiency is pretty high, right? And you also provide us with the suggestion the peak efficiency and the power we should apply for obtaining the highest efficiency. But in my opinion, every approach has a pros and cons, right? So my question is, what's your recommendation when we should apply this approach and when we should not?
Oh, okay, maybe your concern is to utilize this topology or like the device selection and everything as a whole. Yeah. Okay. So
Yeah.
I think it's back again to the application, and I would say maybe you sometimes when you design the power converter, I think you need to pay attention to the, let's say, the target rated power and the distribution of the loss, like also the design of the sizing of your total system. So then from there you can decide the loss distribution and then where the maximum efficiency that you must achieve in your power converter design. And of course, also you need to think about the cost. And sometimes maybe you might allow more loss, or you don't need to have a very high efficiency. So then maybe you will go to the, let's say, just simple inverter circuit without any unfolding circuit and without multi-level. So sometimes maybe you add more power devices and you can achieve higher power conversion efficiency. But then actually maybe your heatsink can be shrink, but maybe the total cost will be higher because you have more power devices. And you will have more component also. Let's say more power devices means you have more gate drive circuits and other auxiliary circuit. So there is more potential for the where the component can go wrong. I mean, so the complexity of the system and everything. I think it's back again to see the application and and the target of the research. Maybe in some application, let's say in aerospace, you don't really think about the cost of the converter, but you really want to push the size to become you want to have smaller size and also lighter weight. So in that case, then you will try to use SiC or other wide bandgap devices, and also try to optimize the PCB layout and everything so that you can have smaller loss. But then for other application, let's say maybe for stationary application, let's say for energy storage and other part, sometimes maybe it's not very critical to have a high power density, also have a lightweight and compact power converter. I mean, I think the judge should be based on the application or product that you want to develop. Or maybe in this case also, if you are in academia, then it depends on your research target. So in this research, our target is to try to push the efficiency as high as possible. So that's why we selected this topology.
Yeah, thank you. So I can summarize that the advantage of your approach is the high efficiency, right? But the disadvantage here is the cost, right? Is it expensive?
In my
compare it to other approaches.
Yes, comparing maybe if you compare with existing product in the market, it definitely will be more expensive.
Yeah. Okay. Thank you very much for your answer, and very nice to meet you today.
Nice to meet you too, and thank you for the questions.
Okay. Okay. So maybe we move some quick question from the Dr. Dai. So please, Dr. Dai.
Okay. Hello, Hadi. Could you hear me?
Oh, hi. Yes, I can hear you.
Okay. Hi, Hadi. Thank you for your very nice presentation. I'm Đại Bùi from Tiêu National University, Korea. So I just have a quickly question. First, this work is inverter involve you have a three level buck, and after that the 8-bit. So the efficiency is very high. I believe your group in Yokohama, Professor
Kawamura.
I believe it is Professor Kawamura, right?
Yes, with Professor Kawamura.
Yeah, it is very famous group about the high efficiency inverter. And I heard that you have a next phase in this inverter, right? Because I heard that the next phase is 99.9%, is right?
Yes, I think they are still investigating. Yeah, still improving the power converter. Yeah.
Okay. So I'm curious. This is the bi-directional inverter. So just assume that in the one way, one directional, but in the one way not fully swap switching. I believe in one way we have only 2 switch is swap switching and 2 other is no swap switching. Am I right?
True. Yes.
But it is still very high efficiency. So I'm very interested. Okay.
Yes.
Okay. And second question is that we have 2 shots, E1 and E2, right? So do we have a relationship between the E1 and E2?
Yeah. I think Prof. Kawamura have done the analysis to find the optimum E1 and E2 to achieve the highest efficiency.
Okay. I
Yes.
understand, because we have E1 and E2, and sometimes we can see that E1 and E2 is not equal, right? So it's not equal. So it's maybe need to the relationship between the 2 shots to optimize the efficiency. So okay, thank you. I understand, and I'm very impressive with this work and your nice presentation. Thank you.
Thank you. Yeah, for the next stage, I think they will try to optimize all of the parameters of the circuit so that we can achieve 99.9%. Yeah. Thank you for your question. Yeah.
Okay, thank you. Very interesting presentation from the speaker. So now I'd like to finalize our webinar. So thank you, Infineon, for the sponsoring this webinar. Thank you, the presenter, and thank you, the audience, for the attention. Thank you, everyone.
Thank you,
Thank you very much,
everyone.
Hadi.
Thank you, everyone. Yeah.
Yeah.
Thank you, everyone.
Yeah. Thank you all very much for joining the webinar today.